This is part 2 of lesson 3 of unit 3, and it is on implicit differentiation. So example 7 says, given x squared minus xy plus y squared equals 7, which is the ellipse shown in the picture, find the equation of the tangent line at x equals negative 1 comma 2. Okay, so the first thing we're going to do is take the derivative, and this is going to be an implicit derivative. So the derivative of the first term is going to be 2x minus, and we're going to use the product rule with the chain rule with the implicit differentiation. So we're going to have y plus x times dy dx. And I did this a couple times in part 1 of the video, so you can watch it there if you're not sure what I did. And then the power chain rule, implicit differentiation on y squared, gives us 2y dy dx, and the derivative of 7 is 0. So taking the 2x, and it's going to be the minus y to the other side, and factoring out the dy dx, we are going to have dy dx is going to equal the 2y from here, and then minus x from here. And that's going to equal negative 2x plus y, or y minus 2x, however you want to write that. So dividing both sides by 2y minus x, dy dx is going to equal, and I'll switch those around, y minus 2x over 2y minus x. Okay, so substituting our point in, we're finding the derivative at the point negative 1, 2. This is going to equal 2 minus 2 times negative 1 over 2 times 2, and minus a negative is going to be plus 1. So dy dx at the point negative 1, 2 is going to equal 4 over 5. So our equation of our tangent line is going to be 4/5 times x plus 1 plus 2. Okay, so if you look at the point negative 1, 2, that is the line that goes along this part. That's a terrible line. Goes along this part of the ellipse. So that's the tangent line there. And now we want to find the equation of the normal line at negative 1, 2. So that'll be the perpendicular line through that point this way. So that's going to be the normal line. Okay, so all we have to do is have the negative reciprocal of the slope. It's at the same point, so we get that line. Okay, moving on to our next example, well actually our next topic, is what if we have to calculate the second and third derivative or fourth of an implicit differentiation. So what we want to remember is the subsequent derivatives will have a dy dx term in them, and so we're going to have to substitute as we go to make sure that our final derivative, and this is important, is only in terms of x and y. There are no derivatives within the derivative. So we'll do example 8 and then 9, which is another ellipse, and we'll see how that works. Okay, so finding the second derivative with respect to x given cosine y equals x, we first have to find the first derivative, and then we'll go from there. So let me move the paper up just a little bit. And so derivative of cosine is going to be a negative sine y And then, of course, using the chain rule, this is going to be times dy dx. And on the other side of the equation, the derivative of x is 1. So solving for dy dx, we're going to get negative 1 over sine y. I know there's a real urge to make that cosecant, but trust me, just when we're doing implicit differentiation, wait till the very end to simplify your trig functions, because things are going to cancel, and it'll just be easier if we don't have to do that. Okay, so now let's find the second derivative. So the second derivative of y with respect to x is going to be, now the one thing I want to remember here is that this is actually negative sine y to the negative 1 power. So when we go to do the second derivative, we're going to have to use a power rule. So we're going to bring the power down, which would be negative 1, so this will become a positive here, and then lower the power by 1. So we're going to have sine y to the negative 2, and then take the derivative of the inside function. So the derivative of sine y is cosine y, and then, of course, using the chain rule, taking the derivative of y, we get dy dx. Okay, so here's where the substitution comes in, because we only want our final derivative in terms of x and y, no dy's dx, right here. We know that dy dx equals negative 1 over sine, so that's what we're going to substitute in there. So now we have, to make this look a little nicer, we have our cosine y over our sine squared y, and now we're going to multiply that times our derivative, which is negative 1 over sine y, and we're going to simplify it even more, and you want to look for other things, other things that you can substitute for. Take a look at the last line that I wrote and see if you can see another substitution we can make. Remember, we want our final answer to be as simplified as possible. So let me write one more line here. So now we have sine cubed of y, and it's going to be negative. So hopefully you'll notice, this is what you want to notice, that this term is x. So cosine y equals x. That's our original function. So that's what we're going to put in. So our final answer, d squared y dx squared, is going to equal negative x over sine cubed of y. So there is our second derivative. So you want to look for those substitutions if you can find them. A lot of times, even without trig functions, other functions, you'll be able to substitute something from the original function back into a second or third derivative. Okay, and then finally, we have another ellipse. So we want to find the points at which the graph of x squared plus xy plus y squared equals 27 has either a horizontal or vertical tangent line. So remember, at a vertical tangent line, we're going to have an undefined slope. So you can see right on the graph, if we look at the graph, we can kind of sketch where these points are going to be. So we're going to have a horizontal tangent line right along there. So we can see there should be one here at negative 3, 6. There is also another horizontal tangent line, since it is a symmetrical figure, here at 3, negative 6. So there's our two horizontal tangent lines. And then there are also two vertical tangent lines, which is like right here. That's not a very good line there. That's better at that point, which is negative 6, 3. Writing that backwards. Negative 6, 3. And then, of course, opposite that here, we have a vertical tangent line at 6, negative 3. So let's go ahead and find those. So let's start by finding our derivative So taking the derivative, we have 2x plus y plus x dy dx. That's the first two terms, and then the derivative of y squared is going to be 2y dy dx, and the derivative of 27 is 0. So factoring out our dy dx and moving our other terms to the other side, we have x plus 2y is going to equal negative 2x minus y. So our derivative is dy dx is going to equal negative 2x minus y over x plus 2y. So here's how we're going to find those points. I wish I'd used green. So for a horizontal tangent line, that means that the derivative has to equal 0. And for a rational function to equal 0, that means the numerator equals 0. So solving this for y, we get y equals negative 2x. So what we're going to do now is we are going to substitute y equals negative 2x into the original equation and solve for x. Okay, so we're going to have, we're doing green, x squared plus x times negative 2x plus negative 2x squared is going to equal 27. And simplifying this, we get 3x squared minus 27 equals 0. So we get x squared minus 9 equals 0. So we have our 2x values at 3 and negative 3, which is exactly what we predicted on the graph. And then for our vertical tangent lines, what we're going to do is set the denominator equal to 0, because if it's undefined, that means the denominator equals 0. So we have x plus 2y equals 0. So y is going to equal negative 1/2 x. And now we're going to do the same thing. We're going to substitute into our equation, and we're going to have x squared plus x times negative 1/2 x plus negative 1/2 x squared, and that's going to equal 27. So simplifying that, you get 3/4 x squared equals 27. So x squared equals 36. So I get x equals 6 and negative 6. So that's exactly as we predicted from the graph. So our final answer is going to be that we have a horizontal tangent line at negative 3, 6 and 3, negative 6. And we have a vertical tangent line at negative 6, 3 and 6, negative 3. And that's the end of section 3.